Hey guys, so I am an educator at Unacademy and you can follow me over there if you're interested to watch videos on basic concepts of chemistry or physical chemistry topics. You can also recommend this to your juniors and to your younger siblings, right? All you need to do is download the Unacademy learning app and watch my videos over there. Now let's just begin with our topic. Hey guys, what's up? Welcome to another video of Raman spectroscopy, and in this video we are going to have a quick recap of the concept because we have not till yet discussed the whole concept of Stokes and anti-Stokes. And let's move this Raman spectroscopy a little forward, right? So till now what we had discussed was, and there was a very interesting doubt that had been asked, that what are these energy levels that I've written down as 0, 1, 2, 3. So these can be vibrational also, these can be rotational energy levels also, and they can be both vibrational and rotational, right? It depends on what kind of Raman spectroscopy you are dealing. So you might have heard of pure rotational Raman spectroscopy, pure vibrational Raman spectroscopy, and rotational vibration Raman spectroscopy. So it all depends on these energy levels. If these are rotational energy levels, then it's called pure rotational Raman spectroscopy. If these are vibrational energy levels, it's called pure vibrational Raman spectroscopy. And if there's mixture of both vibrational and rotational, because in between two vibrational energy levels there are many number of rotational energy levels also, so then it's called rota vibrational, rota by whatever vibro rotational Raman spectroscopy, right? So we are going to discuss that as well. But before that, let's just discuss Raman spectroscopy in detail. So let's say these are the vibration energy levels. All right, let's assume these are the vibration energy levels. So what did we study for Rayleigh scattering or the elastic scattering was that if we have some frequency h mu, and with that frequency the molecule interacts with that frequency, it does not absorb that frequency, it merely scatters that frequency. So what happens is the photon gets the energy from the ground state energy level, it gets excited to some virtual state. It is not a real energy level, it's a virtual state which is very short lived. And then if it returns back to the same energy level, that means it emits the same photons h mu, then it's said to be Rayleigh scattering or elastic scattering. That means the energy that we transfer, the same energy is emitted, right? Or the same energy is scattered by the same energy of the scattered photon we obtain, then it's said to be Rayleigh scattering. If the incident photon and the scattered photon are not of the same energy, so then it's called inelastic scattering, and there are two cases. Okay, one gives rise to Stokes line and one gives rise to anti-Stokes line. So what happens in Stokes is we have, let's say, a photon which interacts with the molecule. From the ground state it gets excited to the virtual state, but it comes back to the first excited state. Instead of returning to the ground state like that happened in Rayleigh scattering, it is returning to the first excited state, right? So that means if we are supplying an energy, or if the photon has energy of h mu, the photon that will be emitted will have energy less than that, because this energy from virtual state to the ground state is more, and the energy from the virtual state to the first excited state is less. So there will be some lesser energy of the photon. So if the photon that is emitted or is scattered will have lesser energy, I am sorry, I am saying emitted again and again, it should be scattered. So the scattered photon is going to have lesser energy, and then this scattered photon gives rise to Stokes line. Whereas if, let's say, a molecule is in the first excited state, it goes to the virtual state, comes back to the ground state. Now the energy of this photon from the that was supplied to this molecule, it got excited from first excited state to the virtual state, whereas once it returned to the ground state. So this energy of the scattered photon is greater, because compared to the energy between first excited state and the virtual state, and if you compare the energy of virtual state and the ground state, this is more. So the energy of the scattered photon is going to be more than what initially was given, right? So that means this will give rise to anti-Stokes line. Okay, so this is the diagram you generally see. This is your Rayleigh scattering, which I represent by wave number, right? So on the x-axis we have the wave number, and on the y-axis we have the intensity. So if you see, the Rayleigh scattering is the most intense, followed by Stokes line, which is towards the left. So always remember, the Stokes line will be towards the left and the anti-Stokes will be towards the right when we are representing in terms of wave number, right? So you should be careful what is being represented on the x-axis. I'll discuss what I mean by that. So why is first of all, let's discuss the intensity, right? I have written down over here intensity. So what exactly, why is that Stokes line have higher intensity than anti-Stokes line, and why is Rayleigh scattering is the most intense? So this is the if conceptually speaking, this is the most elastic scattering, is the most favorable scattering that can take place, and that's why Rayleigh scattering is very, very intense. Because if a molecule gets excited from the ground state to virtual state and it gets scattered, it will return back to the ground state. That is the most probabilistic thing that can happen, and that is why Rayleigh scattering is the most intense. But if we compare Stokes and anti-Stokes at room temperature, okay, I'm talking about room temperature. So at room temperature, what happens is from the ground state it gets excited to the virtual state and then returns to the first excited state. So the number of atoms or the number of molecules in the ground state at room temperature is going to be much more. So that is why Stokes line is intense. Whereas if you see in anti-Stokes, where is the excitation taking place? For the molecules from first excited state, they are returning to the ground state. So the number of molecules in first excited state at room temperature is obviously going to be less than the number of molecules in ground state at room temperature, and the intensity depends on the number of molecules that are getting excited to the virtual state and then getting scattered. So since there are more molecules in the ground state at room temperature as compared to the excited state, that is why Stokes line are much more intense. In fact, they are 100 times more intense than anti-Stokes line, and that is why you need even a better Raman spectrometer for measuring the, or for resolving the anti-Stokes line. Okay, so this is the big reason of the intensity, and that is why I think there was a question in TIFR also this year, that is in 2017 GS 2018, the paper, where they had said that where will you, I think, obtain anti-Stokes line or something like that, at Kanyakumari or at Mount Everest or something like that. The question was there. So Kanyakumari is hot, so there are more chances that you will get a better anti-Stokes line at Kanyakumari rather than Mount Everest, because at Mount Everest temperature is lower, so there will be more molecules in the ground state, whereas in Kanyakumari it's hot, right, compared to Mount Everest. So there will be more number of molecules in excited state, right? So there will be more chances that you will get an intense anti-Stokes line at Kanyakumari as compared to Mount Everest. All right. Now why is it towards the left and why is it towards the right? This is also a very important thing that we need to understand. Okay, and the reason for that is, let's say we have energy, all of you know energy is equal to h mu. Mu is the frequency, so this can be written as hc by lambda, right? And what is wave number? Wave number is basically inverse of lambda, inverse of wavelength, right? So 1 by lambda is equal to the wave number, so we can write this as hc and v and bar. This is the description, or this is the this is how you represent wave number, hc v bar, bar over the v, right? Now out of this, energy, that means is directly proportional to wave number, because c is constant, that is speed of light, and h is Planck's constant, so both of them are constant, so the energy is directly proportional to a wave number, right? Now in Rayleigh scattering, the energy of the incident photon and the energy of the scattered photon both are same, right? In Rayleigh scattering, the energy of incident photon and the energy of scattered photon both are same. So this E naught is basically energy of, you can say, Rayleigh photon, energy of the Rayleigh photon, or the energy of the incident photon. It means the same thing, but we'll take it to be the energy of Rayleigh photon. Okay, the energy of the Rayleigh photon or the scattered photon in terms of Rayleigh scattering. So that energy is going to be greater than the energy in case of Stokes line, because in Stokes line we are having minus delta E. So from the original energy or from the Rayleigh energy, we are subtracting some value of energy to get your we are subtracting some energy, right? We are subtracting some, not delta E, we are subtracting some kind of energy. So that means the energy of the Stokes line is going to be less. Okay, so because the energy of the Stokes line is going to be less, the wave number is also going to be less as compared to the Rayleigh wave number. The Rayleigh wave number is V naught, and the Stokes line wave number is Vs, so that is going to be less. But if we compare the anti-Stokes, in anti-Stokes we are having h mu plus delta E. That means to the Rayleigh photon we are adding, or to the incident photon we are adding some energy. So that energy is going to be greater. So E of anti-Stokes is going to be greater than E naught, or the Rayleigh energy of the Rayleigh photon. That means the wave number of the anti-Stokes photon is going to be greater than the wave number of the original photon or the Rayleigh photon. So that is why VA is coming on the right hand side. If we are comparing the wave number of anti-Stokes is going to be greater, and then we have V naught in between, and then we have Stokes on the left side. Now this is a comparative thing, okay, where we take V naught as the reference wave number. So what do I mean by that is, let's say we are having 460 centimeter inverse, 470 and 480, where 470 centimeter inverse is the Rayleigh photon, is the wave number of the Rayleigh photon. So that means 460 will be the wave number for Stokes photon, and 480 will be the wave number of anti-Stokes photon, right? So that means we'll take this to be 0, okay, we'll take this to be 0, and we'll write over here 10 centimeter inverse, and we'll write over here minus 10 centimeter inverse. Okay, so this is in reference. So we don't write 470, we don't write 470, 480, 490, 500. We just show minus or plus. So that is why wave number, if you see in the Raman spectrometer, you will see that minus 10, minus 20, minus 30, like that. Why is that? Because so that means in the Raman spectrometer you see negative and positive signs. So positive signs represent your Stokes, anti-Stokes line, and the negative signs represent Stokes line. Okay, so you won't see as 460, 470, 480. 470 is the Rayleigh scatter, the wave number of the Rayleigh photon. So that is taken as reference, and if you get at 480, then it will be shown as 10 centimeter inverse, and if you get at 460, that will be shown as minus 10 centimeter inverse. So this is very important for you to understand. But over here I have written wave number. Instead of wave number, if I write wavelength over here, now this is some kind of conceptual questions that can be framed like that. Instead of wave number, if I write over here wavelength, then this graph will invert. Then on the left side we'll have anti-Stokes, and on the right side we'll have Stokes. Why? Because wave number V bar is proportional to 1 by lambda. So that means the one with a higher wavelength will have a lower the one with a higher wave number will have a lower wavelength, right? The one with a higher wave number will have a lower wavelength. So anti-Stokes has a higher wave number but a lower wavelength. So instead, over here, instead of wave number, if I write wavelength, the graph will invert as in the Rayleigh scattering will remain the same, but now we'll get anti-Stokes towards the left and Stokes towards the right. And this is a very, very important thing to understand, right? So do not get confused over here. This is a very important thing. Now what else we need to discuss is just scattering efficiency. So what exactly is scattering efficiency? So scattering efficiency is basically a particle, how efficiently it can scatter a particular wavelength, okay, and that is given by 1 upon lambda to the power 4. Scattering efficiency is given by 1 upon lambda to the power 4. That means that lower the wavelength, okay, don't get confused between wave number and wavelength. Lower the wavelength, better will be the scattering efficiency, right? Lower the wavelength, better will be the scattering efficiency. That means if I use UV region, in UV, if I compare UV visible and IR, UV has the lowest wavelength, okay? UV will have the lowest wavelength, and if it has lowest wavelength, that means there will be better scattering in UV region as compared to visible and IR, okay? So mostly we'll try to do all the mostly all Raman spectrometers will try and focus on UV region to get a better scattering efficiency and to get a better Raman spectra, right? But what happens is in UV region you can also have fluorescence, okay? So instead of it going to a virtual state, it might go to another excited electronic state, okay? So between different energy levels we also have we have electronic levels also, right? E0 and E1. So it can also be there that if you're using in UV region, the molecule might fluoresce. So from 0 it might go to the first excited state and it could show fluorescence and phosphorescence, and that in fact interferes with our Raman spectra. So we do not want that as well. So we have to keep a balance of the wavelength so that we don't obtain fluorescence in the molecule as well. So this is an important thing that we need to consider. What is the other important applications of this scattering efficiency? Well, blue light and red light, if you compare blue light and red light has a higher wavelength and blue light has comparatively lower wavelength, all right? So what happens is N2 and O2 are there in the atmosphere. Predominantly we have oxygen and nitrogen in the atmosphere, and these are very small in size. So because of the scattering efficiency, they are easily able to scatter the blue light, which is of lower wavelength, and they are not able to scatter the red light, because of which what happens is you see the sky as blue. because the small molecules cannot scatter the red light efficiently because of this formula 1 upon lambda to the power 4. But if you compare clouds have very large water droplets. Okay, they are very large in size. So what happens is, water droplets as compared to your oxygen, nitrogen, they are quite large in size, and they are able to scatter almost all the light, and that is why you see clouds as white in color, but you see the sky as blue in color, because oxygen and nitrogen, because of this formula of scattering efficiency, are only able to scatter blue light with some efficiency. They are not able to scatter red light with as much efficiency, and that is why you see the sky as blue in color, right? So I hope you found this video useful, and thank you so much for watching. Do give me your feedback, and thank you.